Professor Ravi Kane for his excellent mentorship in the course Biosurfaces, which I thoroughly enjoyed, and he gave us very good papers to read, and it was really helpful. Professor Peter Tessier, I was a TA for him for 2 semesters. It was great working with him. He is an inspiration, very meticulous about all the things, and progressively aims at getting things better.
And you won the TA award too.
Yeah.
For yours.
And R.A. Chatterjee and Professor Plosky for helping us with the instruments. So Dr. Fuming Zhang for the SPR measurements, Dr. Leonard for allowing us to carry out experiments in his lab. R.A. Chatterjee and Professor Plosky for helping us with the measurements on contact angles. They have got very fancy goniometer, and all the contact angle work was done in his lab. The Department of Energy for funding this research. The past and present lab members of our group. Arpan, and some of them have left, and some of them are here. And friends, and all the most beautiful people of the world. But unfortunately, they are all males.
And Karen.
Yeah, but I might have missed some of them. They are very special, probably.
All right, thank you very much. Let's open it to the floor and have everybody, all the students and faculty who are not on the committee, ask any questions, and we can. Yes, Steve, go ahead.
I have like 8
I
questions.
hope you're all thinking while you're
I have 8 questions, but I won't ask them all. So why does it not work for the large proteins? Is it just large versus small, or is there something else going on?
2 things probably. First of all, once you saturate the surface with TMAO, at a particular temperature, there is a definite amount of concentration you can reach at the surface. You cannot go beyond that, or else it will start crystallizing on the surface. So we tried 22.5 mg per ml of TMAO, which is quite high compared to the solubility and standards. That's the best we can get. So probably the bigger molecules, they basically, if you assume it to be in solution, you definitely think that there will be more TMAO required to protect it, probably. Or they are just knocking, or the TMAO can be replaced by the protein, or it is just not, the concentration is not sufficient. So that's what I could imagine. I really don't know the exact reason for that.
Okay.
Can I follow up with that?
Please, sure.
So TMAO is zwitterionic, right? It has positive and negative charge, but the positive charge may be more buried in the SAM, okay? And so you may be putting a charged surface on this substrate. And so the question is, have you looked at the isoelectric points of the different proteins that you tested? Are they all identical? They're probably not. In fact, I know they're not.
I think for IgG, it's probably on the lower
So
side.
what if I suggested? What if I suggested that you have a negative charge surface here, net negative charge after you add the TMAO? Would that explain the results? Just think about it. I know you can't answer.
That was my follow-up question.
Sorry about that. Sorry.
So, but now you did the experiments at pH 7.4, right? So if it has a net negative charge, lysozyme is not absorbing, right?
Yeah.
So lysozyme definitely has a net positive charge, right?
Mm-hmm.
Okay, so that would be electrostatic interaction. So that doesn't necessarily explain that, right?
So yeah, it's.
Right.
I think it's just the same mechanism which protects the proteins in bulk. So lysozyme is protected in bulk by TMAO. So the exact mechanism, as I pointed out earlier, is not known whether it is electrostatic in nature, but it definitely wants to exclude itself out.
What about the charge distribution, electrostatic potential around that small
So yeah, of
molecule?
course.
What does it look like?
Of course, lysozyme will be positive at the pH we are working on.
The small molecule, TMAO. What's the electrostatic potential?
So TMAO has a pKa value of about 4.5. Okay, so if you go below that pH, it's definitely not going to work. But for proteins, to take it above that range, above 4.5, it seems to work efficiently in solution. And I really can't comment on how it is putting the surface, but the whole idea is from 3D, it is just translating to 2D. If 3D, it has sufficient population to make peptides or these protein molecules stable. It is just translating to 2D. It is sticking onto it, and it doesn't want to get to the protein backbone. That's what I can think of.
Question.
What?
Anybody else at the back?
I'll let George.
Save a few minutes, we'll come to another one. Go ahead.
In the beginning, you had said that with the DMAO surface, you were trying to develop a regenerative,
Louder.
a regenerative protein-resistant surface, but you were showing that not all of the TMAO gets removed. So I wasn't sure exactly what you meant by regenerative.
So, because when we raise the temperature above 40 degrees, we started losing it by the contact angle measurement. So if you go high enough in temperature, it will just be removed, and all the underlying surface will be just CH3 SAM.
So does that have any effect then on the ability to resist the proteins? Like if you remove the TMAO afterward, does it?
So because the TMAO has already left the surface, I won't expect the surface to be different from from the control. Since there is no TMAO, after you bring it to 60-70 degrees, it will probably be all lost, and then the surface is just CH3 SAM. So I don't expect it to be different than the CH3 SAM before TMAO adsorption.
So I'm wondering if you had done that release of TMAO after you had absorbed the protein, if it would then allow the protein to be released more, or
Nothing like that. Yeah, we just functionalized the surface or treated it with TMAO, checked the adsorption, and checked the stability of TMAO. So we did not check I think, as I understood from your question, that you first put TMAO, then the protein, then TMAO again?
No. You're saying that you have functionalized, well, you've sort of absorbed TMAO into the SAM, and then you're testing to see the protein resistance of that surface.
Mm-hmm.
And initially when you suggested that you were developing a regenerative protein-resistant surface, I thought, well, maybe you can, it resists the protein to a certain extent, but then you can remove that layer and then reestablish protein resistance.
So regenerative was used because it is just a non-covalent assembly. It's a self-assembly, so
It's a coating.
It's
just a coat.
Yeah,
And the temperature effect was just to see how stable the coat is. Because if it doesn't work at 37 degrees, what the hell? Wasting your time. So, are there any other questions? Yes.
I have a
He's a co-author of some of this stuff.
I have a doubt more than a question. You showed in the TMAO stuff that the protein is depleted of TMAO. So in the bulk, you will have the protein surrounded with TMAO, and because of the surface, the TMAO is going to the surface and not sticking around the protein. Is it right?
So when the protein solution was introduced, the surface was pre-treated with TMAO.
Okay.
In the protein solution, there was no TMAO.
Okay.
It was just in buffer, and it was introduced in the chamber.
Okay.
And this sensor crystal, which was monitoring protein adsorption, was pre-functionalized with CH3 SAM, and it was kept in TMAO for 24 hours.
Okay.
So the adsorption was, and then it was washed off, and then it was placed inside the chamber.
Okay.
Yeah.
Okay, Steve.
Can you explain?
We're waiting for you.
What's this? Okay. I'm not going to ask too many more. Can you ask?
No, you can go ahead.
So the composite index, right, where it's the random and the helix together.
Mm-hmm.
Tell me
Just
why
to say,
that.
normalized by molecular weight.
Fine. But even still, so now tell me why that should be an important parameter, and why would that work for all proteins? Because there's different ways of proteins associated.
Exactly, you're very right. I mean, that's the general trend which was observed. It's not a thumb rule. It was so Anand Seturaman, he did protein-protein interaction studies. So he had proteins grafted on the surface. He had protein grafted on the AFM probe, and then he checked the interaction of those two proteins. So he took a library of about 9 or 10 proteins, and he saw that interaction increasing with random and helical content in the proteins. So once you have seen that there is high adsorption on the surface, protein-protein interaction seems to be dominant. And that was the index which is primarily previously shown to match well with the protein-protein interaction. So that's why that was the justification for using.
But tell me from a fundamental perspective why that should be the case.
Okay, so there has been many studies in the past where the compressibility of proteins is related to the stability. So there was a very famous paper by Gecko where they checked the compressibility using sound waves, and it was seen that protein which has higher amount of alpha helical content was more compressible and less stable than proteins with higher beta sheet content on the surface also. So yeah.
So this is the first sort of parameter. It's a gross parameter. It's not specific to any protein, but it gives you some idea in a rough way whether a protein is easy to unfold or not going to unfold. And I've never seen it anywhere else, actually.
Yeah.
So it's the first time Anand did it about 5 years ago, and we checked it here, and it seems to fit beautifully again.
But whatever's not random or alpha helix, this beta sheet or beta turn, right?
Well, you could put 1 minus.
Right, exactly.
It's like
yeah,
everything
right,
in
right,
life.
Exactly.
Okay, Chip, anybody else, any of the students, or are you all asleep here? Are you with us? Any questions up there? We had one nice question. Let's get some others. None? All right, well, thank you all for coming.